I came across another text that didn't do a really good job for presenting pointers. I got really frustrated, so I decided, okay, I want to talk about pointers because a lot of people get confused about this, and I think there's a really great way of explaining the concepts that really unravel a whole bunch of mystery around pointers and memory management, and how to think about them. Okay, so if I give you this line and I ask you, what does this line actually do? It's a seemingly very simple line. You have an integer called number, you have a number of type integer, it gets value of 42. The reality is that this line probably does a whole lot more than you actually expect. And if we unpack this just one line, we're going to get to see a whole lot more in terms of what's going on with pointers. And it's important to really understand what's happening here. Okay, so what's actually going on here is like this. First of all, you need to request enough memory to be able to fit an integer. That's what that int is actually saying. He's saying, hey, give me enough memory to fit an integer's worth of data. What we're going to then do is we're going to give an alias, sort of an alias, to that memory location that the computer gave back to us. And then what we're going to do, at that memory location that was given to us, we're going to go ahead and store the value 42. So if we look at this int here, what we can actually think of, we can almost think of it as some kind of a function. What is that function? It says allocate memory. How much memory should I allocate? Enough to fit an integer's worth. On most computers, that's 4 bytes, and some is going to be 8 bytes, but it's enough to fit in integers. And what it's going to give you back, it's going to give you back an address. So something like this. Imagine an address of 0x123abc. This is actually true on any programming language in almost any computer you will ever come across. When you say, I need this amount of thing, whatever language it is, Java, C, C++, Go, doesn't matter. It allocates the amount of memory and it returns back behind the scenes a memory address where that box of memory was allocated. Now, we don't know where that memory address is. And if we had to write a program always using like static addresses or even like finding some kind of a language for working with addresses, it would be really inconvenient to do something like this, like 0x123abc gets the value 42. Like that just would be odd, and none of us would want to be programmers for very long. So what programming languages have done now for 60, 70 years is that they effectively give us an alias. And what we're doing is we're aliasing the name num to that memory address. So that whenever you type num, behind the scenes, the computer resolves, the program resolves this to say, hey, actually go to this memory address and then read and write the values straight from that memory address. How are you going to treat those values? Well, you're going to treat them as integers. And that's what's going on there. So behind the scenes, whenever you write num, the program is going to take that num and is going to translate it to 0x123abc or whatever the address is. And then it's going to do something with it. It's going to read some value from it, or it's going to put a value into that memory location. This memory address changes every single time you run the program. So it's really inconvenient for us to have to manage it or hold on to it or like actually know what it is. Finally, we're going to put all of these pieces together. So we're going to look up the memory address that num is associated with. We're going to check, hey, is it big enough to store the value we're trying to put into it, which is a 42, and 42 is an integer. And we're going to say, yep, we've allocated an integer's worth of memory at this location. And what we're going to do, we're going to go ahead and write that value, the value 42, at that memory location. So if we imagine a box somewhere in memory, both of these things are true. Actually, all three of these things are true. Inside of that box is the value 42. How to get to that box is a memory address somewhere in your memory. And that address is 0x123abc. But you could also call it num. And that's a much more convenient way of going to that memory address than actually having to know that it's 0x123abc. So what does all of this have to do with pointers? So far, we haven't really talked about pointers. We haven't really talked about what they are, how to work with them, or what's going on here. This is actually really fundamental because whenever you're allocating memory, whenever you're creating a variable, you're always dealing with memory. And pointers are the language of memory. That's how we talk about memory. That's how we discuss memory. And we'll talk a little bit more about later on. So every variable you ever create in a program, doesn't matter what variable it is, doesn't matter what programming language it is, it will always have an address. Even in Python, like the most dynamic of languages, if you just create an object and you output it and it doesn't define its quote-unquote string representation, the default thing it's going to print out on the console is going to be its memory address. So that's effectively what you're doing with any variable in any programming language. You're allocating enough memory or some way of storing the data in it. That memory address. So here's my question to you. So far we've written values, or we looked up values. We looked up the value 42. We stored the value 42 in the memory address. What if we actually wanted to change the question? Just like hypothetically, let's humor ourselves. As opposed to the value of num, what I really wanted to know is like, okay, I have a bunch of memory, but I'd like to know where in my memory is num located. What I want to get at is the actual address of num. Like, where is it in memory? We'll get to the reason why in a bit, but let's just start with this question. Strange. I know if up to this point you've only ever worked with values. I have a string, I have a number, I'm just dealing with the values. Like, why would I want to know? Why would I want to care what the address of it is? But let's humor ourselves. Let's just say we want to know where is the address in memory of this variable. So the way to do that is using this really strange operation. So let's take a look at some C++ code. We'll take a look at C code. They're pretty similar. So if I was to run this program, the first line over here is going to execute, is going to print out 42, and the next line is going to print out the address of num. And if I was to do the C code equivalent, it's pretty much the same thing. The first line will print out the value num, and the second line will print out the address. And the question you need to be asking, what in the world is this ampersand doing here anyway? What is this ampersand thing? What is this weird character that I'm putting in front of the variable? So the best way to think of it, and this is true for C and C++ and Go, is that the ampersand is the address of operator. The way to think of it is that it's its own type of function. If you remember in the beginning, we said that when you have a data type, you can think of it as saying, hey, give me some memory big enough and give me back an address. And then behind the scenes it gets alias to a variable name or whatever. The ampersand operator is sort of similar, but in this instance, as opposed to me saying, here's a data type, like integer or string or whatever, and allocate enough memory and tell me where it is, in this instance, I'm actually giving you a variable, and I'm telling you, so like, by the way, where did you allocate that? Where did you put this variable that I just created? It's a little bit of the reverse process. So you can think of it as almost like this function, the address of function that's going on behind the scenes. So whenever you're reading and you see this ampersand, pretend you're reading out loud, the address of num, or the address of blah is this, and it's going to give you back a memory address. So this function, this mythical function, doesn't actually exist. It takes in the variable and it returns where that variable is stored in memory. So instead of ampersand num, pretend it's actually the address of num. That's like the big mental shift. So whenever you see an ampersand, pretend it's just address of num. That's what's actually going on. It's its own function. It's giving you back the result. So what the ampersand of is doing, it's giving you back with the address. So if this was your memory location and this was where num was pointing to and there was the value 42 there, it would give you back the address. Now, here's the question. I have an address and it's giving me this address, but what's the data type of this address? Like, how am I actually going to store it? What kind of variable do I need? Like, what do I put it into? Because if you saw, I very sneakily didn't store the value of the address. I just printed it out. And both C++ and C handled it nicely. The C++ version totally was cool with me passing an address value to cout. And C just simply said, hey, this is a P, right? If you remember, this was a %P. A %P is a pointer. Interesting. That's what we got. Curious. But what if I wanted to store this somewhere to be able to use it later on? That's where we get to pointers. A pointer is a generic name for the data type. And what that data type contains, it actually contains an address. As opposed to containing some interesting value, it contains an address. But we're going to look at it a little bit more closely now. So you remember this. Int num is equal to 42. You saw this line way at the beginning of me talking and rambling on here. And if you remember this, the data type of num, the kind of data being stored at the memory location associated with num, is an int. Int is the data type of num, which means if you go to the memory location of num, and as we mentioned earlier, every variable has a memory location, what you're going to find there is going to be an integer. So that's what the data type is. It's simply telling us that if you went to this memory location, what you're going to find there is going to be an integer. So how do we define a memory address data type? How do we define something that can store memory things? Notice that here we're storing values. It's the value 42. And if we wanted to get the address, well, we would need to do that operation. But how do we store that value? Because you couldn't store it in int. It's not an int anymore. It's a memory address. That's where the pointer comes in. That's where that fancy star comes into play. The star means that at the num pointer memory location, wherever you go to num pointer, you'll find an address. And if you follow that address, you'll get to an integer. Now remember what we said earlier. Every single variable has a memory location. So even when we write int pointer num ptr, we've allocated some memory in some memory for us. How much did we allocate? To be able to store enough for an int pointer. And an int pointer is just an address. So enough to be able to store an address's worth of memory. On most modern systems, that's usually 8 bytes because they're 64-bit systems. Won't get into that right now. But it's 8 bytes to store an address. So if you go to that place in memory, what you'll find is not a value where numptr is. What you'll find stored in there is an address. And if you were to then say, okay, I want to do something with this address, because an address is just sort of a mostly useless thing, if you were to then follow that, what you'll get to is an integer. And that's this part in front of the star. That's the int in front of the star. It's telling us that if you were to follow the contents of the pointer, what you'll get to. And this is true if we had a string pointer, or if we had a double pointer, or if we had a car pointer. What it's telling us is that in that box, there's going to be an address. And if you follow that address, you're going to get to a car, or a string, or an int, or a double. So how do we define a memory address data type? We actually sort of saw that. So, sorry, going back. So a more visual representation of this would look like this. So imagine you have numptr somewhere in memory, and it itself has its own memory address, 0x111AAA, and in that memory location, you have an address, 0x123ABC. And if you were to follow that along, you're going to get to num, which has the value 0x123ABC. How do we do that, right? This is the mapping of what's going on here. The C++ code over here is just to demonstrate this. So we can print out, if we had a numptr variable, we can print out its address. And it should print out 0x111AAA. Then, because numptr, as we defined it earlier, is a pointer, we can assign to it an address. Remember, the address of operation gives us back an address. So num is an integer in memory, but it has its own address. But we take that address and we put it inside of numptr. In the numptr memory location, we store the address of num. And now what that means is we can go ahead and print out numptr. We can actually put it onto the console and say, here you go, there it is. That's that second C outline. What it will do is print out 0x111AA. So it will print out, 0x123ABC, because that's the contents of that memory location. Now, if we were to follow along and jump to the other side of it, and that's where the star here is, we'd get to the value 42. That star is called the dereferencing operator. What it's actually saying is, okay, now take the memory address and then go to that location and give me the value that's there. It's following that line. It's following that pointer that you're seeing up there. Imagine, as opposed to an arrow, there was a physical finger pointing at that location. That's why it's called a pointer. And if I ran this on my machine, I have a small code. I'll make sure that it's linked up in the description here. You can see that it's the value of num, the address of num, then we have the address of numptr, of where it's in memory. But then we stored the value in numptr of num. You can see that's the fourth line. And when we dereference it, we get back the value of num. And the exact same thing is true if we were to do a C code. It looks exactly the same, just the printfs effectively change, but no other major difference. And this is effectively what it looks like with the C version. I added a little bit more text in here to make it clear, but it's effectively the same thing as the C++ one. So now we have to sort of pause for a moment and just understand the difference between the ampersand and the star. The ampersand, when you're declaring a variable, that's not really allowed in C, but you can do it in C++. It does a reference allocation. But when you're doing it in instruction, you can think of it as the address of operator. It's going to give you the address of whatever variable you're dealing with. On the other side of it, the star, when you're declaring a variable, what you're actually doing, you're declaring a data type. You're declaring a new data type, a char pointer, an int pointer, a string pointer. Ultimately, they're all going to be the same size because they're all storing memory addresses. Memory addresses are fixed size. And then when you're using it as an instruction, what we saw over here in the dereferencing side, over here in that last line, what it does is that it goes to that memory address that's stored in this variable, and it gets the value out from there, and it prints that value out. That's a lot of moving pieces here, I get it, but I feel this is a better explanation than many other ones have done this. Now, the biggest question I had when I was learning this whole pointer thing many years ago at this point, it seemed to be wasteful. I was like, why would I want to allocate more memory just to store a memory address of an int? Because everybody gives this int example, and I just committed that crime as well. The reason being is that when you're dealing with much larger objects, let's say a car, something that represents a car, or an account, or a shopping basket, or a home address, or something of that nature, something that's way more complicated, or an image, or a sound file, or a movie file, moving around those variables that actually contain that data around becomes very expensive. It could even be just outright prohibitive to do that. While moving pointers around, well, you're just moving memory addresses around, and that's pretty easy to do. So it's easier to move around pointers than big objects, big blobs of strings, text, images, movies, so on. Not only that, many algorithms are simple or more efficient to implement with pointers. If you're doing a sorting algorithm or a searching algorithm, it's actually easier to jump around with many data structures that we'll potentially examine later on, just jumping memory addresses, than it is to copy things over. But there's also a really fascinating reason is that sometimes you want every single part of your system to actually see the exact same state. So imagine you have an account, a user's account, and you modified something about that account. Let's say you modified their name, or you modified their expiration date, or you modified the password, or whatever, credentials, or provisioning, whatever else. If you copy that account around, you will have different versions of that account, even though many parts of your system need to actually really see the exact same thing. So it's much more important to just move the pointer around. It's safer and more correct than it is to move the physical objects, because then you can get into sort of like this weird state. And I'm sure every one of you has used some kind of weird application where you change the username in one place, and then for whatever reason you go back to the original, some other state, and guess what? For better or for worse, you just like don't have the thing that you changed. You don't your profile picture isn't updated, or your name isn't updated, or your phone number isn't updated, or some other settings. That most likely has to do with more of databases than anything else, but fundamentally, in terms of a conceptual model, you have multiple copies of the same data, and they're not all synchronized. Being able to pass a pointer to the one single version view of the object is one way to avoid this problem. So pointers are a great solution to that problem. Okay, this is sort of my presentation of the material. Really what I wanted to get across is that everything is really a memory address. Everything has a memory address. And what a pointer is, what this thing is at the end, is that it's just a box that contains an address. And if you were to go and follow that address, what are you going to get to? You're going to get to a thing is that of that type to the left of it. That's really, honestly, the most simple thing to remember. We'll cover more. I'll probably do another presentation on how to work with pointers, how to pass them around to functions, how they're applied. But I wanted to get this out of the way because this is yet another instance where I saw a text that was written by great authors, but they, in my opinion, botched it and just didn't do a good presentation of this yet again. And I wanted to give on this my twist that I found works for many people. Okay, more of this following along, and then I'll present more of these talks.